Alrighty, so now that we've been through a few of the chromosome mutations, mostly rearrangements, we're going to jump to another major type of chromosome mutation called aneuploidy. And so aneuploidy can come in four different varieties, which we'll talk about in just a little bit. But in a more general sense, aneuploidy is where we see a change in the total number of individual chromosomes that are present for an individual. And so usually this results in either a reduction in total chromosomes or an addition in total chromosomes. And it can happen in either mitosis or meiosis. And usually in meiosis is where we see the centromere actually being lost. Another condition that results in aneuploidy is the concept of non-disjunction. So non-disjunction can happen at two major places, meiosis 1 or meiosis 2, and this is where chromosomes just fail to separate. So in meiosis 1, we've got two copies of two chromosomes, and as we move from meiosis 1 into meiosis 2, we're supposed to be reducing down the total copies of chromosomes from a 2N to a 1N individual. Okay, so but with non-disjunction, what happens is we get failure of separation during anaphase, so one cell ends up with all the genetic material and the other cell ends up with no genetic material. So then as you proceed through meiosis 2, even if it's normal, we're going to get double the amount of genetic information that should be there compared to normal. And then after we go through the fertilization process, you actually end up with 3 copies of genetic information. So 2 from the non-disjunction happening in meiosis 1, or so if this was like mom's cell versus dad's cell, you'd have 2 copies of mom's DNA for that chromosome, and then fertilization would bring in a 3rd copy from dad. So this results in a trisomic zygote with 3 copies of genetic information, and usually we would get a complementary cell like that, but in this case, with non-disjunction happening in meiosis 1, we get a monosomic zygote. So what the second major area that non-disjunction can happen is in meiosis 2. So meiosis 1 can actually progress pretty naturally, no major problems, but we can see non-disjunction happen, or a failure of chromosomes to separate, normally in meiosis 2. So one cell ends up with 2 copies of genetic information where there should only be 1. So as that organism goes through the fertilization process, we end up with 1 cell that has 3 copies of genetic information, 2 from non-disjunction and 1 from the new DNA coming in. And then we get 1 cell with only 1 copy of genetic information. Then we'll get 2 other cells that are normal. They're normal and diploid. So non-disjunction can also happen in mitosis as well. So, and this is where we see failure of separation to actually take place. So if we've got 2 different chromosomes, think about this as chromosome 1 and chromosome 2 in red and blue respectively. And as we go through the mitotic process and non-disjunction happens, the second chromatid of chromosome 2 did not separate normally, so both chromatids ended up staying in that cell, in addition to 1 copy of the chromatid number 1. So as we go through the copying process in mitosis, we get lots of cells with 3 copies of genetic information, or a trisomic somatic clone. And then we get a monosomic clone of cells that only have 1 copy of genetic information in it. So non-disjunction really leads us into the major, or 2 major diseases that we're going to talk about in just a little bit. But again, stepping back out to a more broad sense, let's look at aneuploidy in general. Aneuploidy can happen one of 4 ways. It can happen as a nullisomy relationship, where both members of a pair of homologs are lost. So this is where we see a 2N or diploid cell actually being completely lost. So they're losing both copies of genetic material. So null means loss. Keep that in mind. The second type of aneuploidy is monosomy, and that's just what we saw in non-disjunction. So this is where we see a loss of a single chromosome. So our normal diploid cell is going to be losing one copy of one chromosome. And then we can also see trisomy happen, and this is where we switch gears and we have an addition of genetic material. So a diploid chromosome plus another copy of genetic information results in a triploid. Okay, so that's trisomy. And then tetrasomy is an addition of two more copies of genetic information. So those are the types of aneuploidy that can actually take place. So an example of this that we see is in Jimson weed. You guys may have be used to or familiar with this. So Jimson weed, again, don't smoke it. It's actually very popular in the Southwest and the desert regions. And there were a group of high school kids outside of El Paso that were partying one night and decided to try to smoke it, and then everybody died. So again, stay away from Jimson weed, okay? But regardless, this weed has 12 pairs of chromosomes. And so each pair of chromosome actually results in a different phenotype of seed case. All right, so one of the other types of aneuploidy that we're more familiar with is trisomy 21. So we've got an extra copy of genetic information on the 21st chromosome. And this is classified as primary Down syndrome. So out of, or a total of 92% of Down syndrome cases actually have 3 full copies of chromosome 21. So if we look at our karyotype here, we've got chromosome 1 up here towards the top, and down towards the bottom we've got chromosome 21 and 22. And if you see chromosome 21 here, oh, I did not highlight it, that's okay. We can actually see 3 copies of chromosome 21 occurring in this individual. So this condition usually arises because of non-disjunction during egg formation. Okay, so this is very much a condition that is related back to the female. And then in addition to that, 75% of the non-disjunction events are going to be maternal in nature. And most of those are going to occur in meiosis 1, and very few of them actually occur in meiosis 2. So the caveat to this is that we now have some ways to manage it, and we now know more about the syndrome, and it actually will occur in women that get pregnant and have babies at a higher frequency over the age of about 38. So we've got a graph here that shows the maternal age, or the age of the mother, on the x-axis, and on the y-axis is the number of children that are afflicted with Down syndrome. So we've got pretty normal rates through the 20s and through the mid-30s, and then we start to see an increase in individuals that have Down syndrome if their mother is over 38 years of age. So a common practice now, as a part of the neonatal process, is to do screening if you're 38 years old and pregnant. Because there's some things that people need to prepare for at this point in time. So 4% of the Down syndrome cases actually have 46 chromosomes. So this is 46. It's supposed to be 45. I'm sorry. 45 chromosomes. So 21 right here. There's only one copy of it. And so what ends up happening is sometimes we start to see. Sorry, no. I'm misreading things. Okay, so in 4% of Down syndrome cases, they do have 46 chromosomes, so that's different than what we just looked at. Okay, but where we still see the Down syndrome phenotype happening or syndrome happening is because part of this chromosome 21 actually went through a translocation process. So remember, translocation is exchange of genetic material between non-homologous chromosomes. Okay, so we can actually see a part of or chromosome 21 attaching to part of one of the chromosome 15s. So that will still result in an individual with Down syndrome, but this is what we call familial Down syndrome, because as these individuals become pregnant or procreate, they're going to pass on that translocation on chromosome 15. So our translocational carriers that have only 45 chromosomes are still 45 total chromosomes are still normal, but 15 just tends to be attached to 21. So all the chromosomal material is still there, just the way that it's regulated is much different. So the way that Down syndrome actually occurs is shown in this graphic. Okay, so we've got the P generation or the parent generation at the top. That is going to be in the yellow, and we've got the F1 generation or the generation of offspring below. So we can see if we have a parent that is a translocation carrier, so they've got one copy of 21, then they've got a copy of 21 attached to 14, and then they've also got a normal copy of 14. So non-disjunction is going to take place, and as we go through meiosis and mitosis, and then fertilization, meiosis 1 and 2, and then fertilization, we get zygotes that are going to have these different types of copies of DNA. So, over half of the individuals that end up with zygotes that are translocation carriers and normal individuals live. Okay, so we get a third of offspring that actually have Down syndrome, and they live through birth. However, if we get individuals that have either a monosomy, a trisomy, or another monosomy, genetic or copies of genetic information, those usually tend to be lost in utero and are aborted as a miscarriage. So just keep that in mind as we start working through trisomy 21. So again, just a few aneuploids on the autosome. So autosomes are non-sex chromosomes. So a few aneuploids besides trisomy 21 result in human live births. Usually everything else is spontaneously aborted. So trisomy 13, usually those individuals usually die by the age of 3. And trisomy 8, only 1 in 50,000 births actually make it to a live birth. And there's also trisomy 18 that very rarely make it to a live birth. I actually know some people that had that happen, and their little girl lived for exactly an hour after birth. It's very sad.